I'm going to present a work on computing optimal repairs for functional dependencies. This is a joint work with Benny Kimmelfeld and Sudeep Roy. So we'll start with a very short background, and then I'll talk about the problems that we studied in this paper. Okay, so in this work, we consider inconsistent databases, which are databases that violate a given set of constraints. In our case, the constraints are functional dependencies. Okay, so here we have an example. We have a database that stores information about locations of offices in a company. And we have two functional dependencies. And you can see that this is an inconsistent database because, for example, we don't know if the headquarters is located in Paris or in Madrid. So there are many, inconsistency arises in many different situations. Okay, for example, when we integrate data from different data sources that disagree with each other, or when the data that we use contains errors, or when the data collecting process is imprecise, like in natural language processing, and so on. And there are two main approaches to handling database inconsistency. The first one is database cleaning, where the goal is to remove the inconsistencies from the database. And the second one is consistent query answering, where we do not remove the inconsistencies, but for each query, we only want to return the answers that are not affected by inconsistency. Okay, the answers that will appear in every possible repair of the inconsistent database. So in this work, we consider two types of repairs. The first one is subset repairs, which are obtained by deleting tuples from the database. And the second one is update repairs, which are obtained by changing values in the database. And then an optimal repair is a repair obtained by a minimum number of operations, okay, a minimum number of tuple deletions or a minimum number of value updates. And we also assume that each operation has a weight, but I will give the formal definitions later. So there are two main reasons why we need optimal repairs. The first one is that if we have an automated system for data cleaning, then an optimal repair is a good candidate. We can use it to clean the database. But even if that's not the case, we can use the distance of an optimal repair from the original database, or the number of operations required to obtain this optimal repair, as a measure of inconsistency, okay, or as an indication to how far away we are from a clean database. Okay, so I'll start with the problem of computing optimal subset repairs. And we'll start with the formal definitions. So a consistent subset is a subset of the tuples that satisfies the functional dependencies. Okay, so here we remove tuples to resolve the inconsistencies. So for example, we can remove the first tuple. Now we know that the headquarters is located in Madrid, and this is a consistent subset. So an optimal subset repair is a consistent subset such that the distance of this consistent subset from the original database is minimal among all possible consistent subsets. Okay, and how do we measure the distance? So we assume that each tuple in the database is assigned a weight that represents how costly it is to remove this tuple from the database. And then the distance is just the total weight of the tuples that we removed from the database to obtain this consistent subset. Okay, so for example, here we remove the first tuple, and the weight of the first tuple is 3, so the distance here is 3. Okay? If we take another consistent subset, so here we remove 2 tuples, the weight of each one of them is 1, so the total distance is 2. And this is actually an optimal subset repair because we cannot do better than 2. So in this work, we study the complexity of the problem of computing an optimal subset repair. Okay, and it is already known that there exists a set of functional dependencies for which computing an optimal subset repair is NP hard. Okay, but this is not always the case. And we have an algorithm that computes optimal subset repairs, and I'll show you how it works using the example. Okay, so if you look at this set of functional dependencies, you can see that the facility attribute appears on the left-hand side of every functional dependency in this set. So we call this a common left-hand side, or common LHS. So this means that if we take 2 tuples that do not agree on the value in the facility attribute, they will never violate any functional dependency in this set, right? So what we can do in this case is we can split the database into blocks of tuples that agree on the value in the facility attribute. So here we'll have 2 blocks, one for HQ and one for lab 1. And we can solve the problem separately for each one of these blocks. Then we can just take the union of the results that we have for each block, and the union is an optimal subset repair for the original problem. Okay? So now we have to find an optimal subset repair for each one of these blocks. Okay, so the second one just contains one tuple, so it's already consistent. So let's focus on the first one and try to find an optimal subset repair for the first block. So this is our new problem. Now, since all of the tuples in this block agree on the value in the facility attribute, because this is how we created this block, then we actually no longer need the facility attribute in our functional dependencies to solve the problem for this database. Okay, so we can now remove the facility attribute from the functional dependencies, and this is the new problem that we have to solve. Now, if we look at this set of functional dependencies, we can see that it contains empty set implies city. This means that all of the tuples in the database must agree on the value in the city attribute. Okay? So we call this a consensus functional dependency. So what we can do in this case is actually very similar to what we did before. We can again split the database into blocks of tuples that agree on the value in the city attribute, and we can solve the problem separately for each one of these blocks. But now we'll not take the union of the results that we have. We just need to choose one of them, right? Because we need one value for the city attribute, so it will either be Paris or it will be Madrid, but it will not be both. So we'll just choose the best option, the one with the lowest cost. Okay. So again, we have to find an optimal subset repair for each one of these blocks. So let's try to find an optimal subset repair for the second block. So this is our new problem. But now again, since all of the tuples in this database agree on the value in the city attribute, we no longer need the city attribute in our functional dependencies. So we can actually now remove the first functional dependency from the set, and this is the new problem that we have to solve. Okay, and we can continue in exactly the same way. Okay, we again have a common LHS, and then we will again have a consensus of D. But actually, this database is already consistent with respect to this set of functional dependencies, so we can just finish here. So common LHS and consensus of D are actually simplification steps, right? We use them to simplify the problem, so we can then solve the problem for a smaller database and a smaller set of functional dependencies. We also have another simplification step, and to show you how it works, I will need to adjust this example a little bit. So let's assume now that we have two attributes for the facility. Okay, we have the facility ID, EFID, and we have the facility name, the F name. And so assume that we now also have two new functional dependencies in the set. FID implies FName, and FName implies FID. So because we have these two functional dependencies in the set, we know that the closure of the FID attribute and the closure of the FName attribute under this set of functional dependencies are actually the same. Okay? And we can also see that each one of the other functional dependencies in this set contains the FID attribute on the left-hand side. So we call this left-hand side marriage, an LHS marriage. And what we can do to solve the problem in this case is we can use a reduction to the problem of finding a maximum weighted matching in a bipartite graph, which can be solved in polynomial time. And I will not give the full details, but the idea is that we have to find the best matching possible between values in the FID attribute and values in the FName attribute, because we have these two functional dependencies. FID implies FName, and FName implies FID. So we have three simplifications: common LHS, consensus of D, and LHS marriage. And we have this simplify algorithm, and what it does, it just takes a set of functional dependencies, and it applies these simplifications over and over again until we either have an empty set of functional dependencies, in which case the algorithm will return true, or we have a non-empty set of functional dependencies, but we can no longer apply any simplification. In this case, the algorithm will return false. So it turns out that this algorithm actually captures exactly the cases where computing an optimal subset repair can be done in polynomial time. Okay, so what we have is the following dichotomy for the problem of computing an optimal subset repair. So if we have a set of functional dependencies delta, then if simplify on delta returns true, we can find an optimal subset repair in polynomial time, like I showed you in the example. But if simplify on delta returns false, then the problem is not only NP-hard, but it's also APX complete. Okay, which means that we do have a constant ratio approximation for the problem, but we cannot do better than some constant. And I will later show you an application of this result where this is actually significant. Okay. So this result is on the problem of computing an optimal subset repair, but interestingly, it has applications on seemingly unrelated problems. Okay, and I will talk about these problems now. Okay, so let's move on to the problem of computing an optimal update repair. And again, we start with the formal definitions. So a consistent update is an update of the database that satisfies the constraints. Okay, so here instead of removing tuple from the database, we change values. Okay, so for example, we can see that the first two tuples agree on the facility and agree on the room, but they do not agree on the floor. So we need to change at least one value. So we can change this value, and now the problem is fixed. But this is still an inconsistent database. Okay, so we change some more values, and now we have a database that satisfies the functional dependencies. Now, an optimal update repair is a consistent update that has the minimal distance from the original database. Okay, and how do we measure the distance in this case? So we assume that the cost of changing a value is the weight of the tuple that contains this value. Okay, so for example, we change two values in the second tuple, and the weight of the second tuple is 1, so the cost of changing each one of them is 1. And we change one more value in the third tuple, and the weight of this tuple is also 1, so the cost is again 1, and the total cost, or the distance, is 3. Okay? If we look at another consistent update, so here we know that the headquarters is located in Madrid, but we now know that there is actually another facility that is in Paris. So here we changed one value in the first tuple, and the weight of the first tuple is 2, so the total distance is 2. And this is, again, an optimal update repair. So it is also known that computing an optimal update repair is NP hard for some sets of functional dependencies, but again, this is not always the case. And here I will start with an example as well. Okay, so assume that we have this set of functional dependencies. ID passport implies country, ID country implies passport, and state city implies zip. So you can see that the first two functional dependencies in this set do not share any attribute with the last functional dependency in the set. Okay? So what we can do is we can split this set of functional dependencies into two sets of attribute disjoint, into two attribute disjoint sets of functional dependencies, and we can solve the problem separately for each one of them because they do not affect each other. Okay. Now, if we look at each one of these sets, we can see that each one of them contains a common LHS, right? Because the ID attribute appears on the left-hand side of every functional dependency in the first set, and the state attribute appears on the left-hand side of the only functional dependency in the second set. So we have another result that says that if we have a common LHS in the set of functional dependencies, then the problem of finding an optimal update repair has exactly the same complexity as the problem of finding an optimal subset repair. Okay, so we can use the results that we have for optimal subset repair to solve the problem in this case. Okay, so what we can do is we can use the simplify algorithm that I showed you before. Okay, so for example, on the first set of functional dependency, if we run the simplify algorithm, so first of all, we have a common LHS, the AD attribute. And after removing the common LHS, we have an LHS marriage because we have passport implies country and country implies passport. And then if we remove the LHS marriage, we have an empty set of functional dependencies. Okay, so the simplify algorithm will return true, which means that we can find an optimal subset repair in polynomial time for this set of functional dependencies. And because we have this common LHS, we now know that the two problems have the same complexity, and we can also find an optimal update repair in polynomial time for this set. Now, for the second set, we do exactly the same. We use the simplify algorithm. Okay, so we have a common LHS, and then we have another common LHS and a consensus FD, and we finish with an empty set of functional dependencies. So simplify again will return true, and we know that we can find an optimal subset repair in polynomial time. So we can also find an optimal update repair in polynomial time because we have the common LHS. And finally, because we can solve the problems in polynomial time for each one of these sets, we can also solve the original problem that we have in polynomial time just by combining those results. Now, if we take the second functional dependency in the set, the ID country implies passport, and we just change one attribute, for example, to ID country implies language, then now if we try to run the simplify algorithm on the first set, after removing the common LHS, it will get stuck. We can no longer apply any simplification on passport implies country, country implies language. So because the simplify algorithm will return false on this set of functional dependencies, we know that computing an optimal subset repair for this set is APX complete. And again, because we have a common LHS and the complexity is the same, we know that computing an optimal update repair is also APX complete. And so the original problem from the original set of functional dependencies is APX complete. Okay. So for update repairs, we do not have a full dichotomy like we have for subset repairs, but we do have some general tools, some general techniques for analyzing the complexity of the problem. Okay, so for example, we show reductions between different sets of functional dependencies, and we show reductions from the problem of computing an optimal update repair to the problem of computing an optimal subset repair, and vice versa, like I showed you in the example. So we have cases where the two problems have the same complexity. Then we ask ourselves the question, do the two problems actually have the same complexity for every set of functional dependencies? And we show that the answer to this problem is negative and that the two problems are incomparable, okay? Which means that we can find the set of functional dependencies for which finding an optimal subset repair is easy, but finding an optimal update repair is hard. And we can also find another set of functional dependencies for which finding an optimal subset repair is hard, but finding an optimal update repair is easy. Okay, and finally, we'll also talk about approximation. So there are still many open problems for update repairs. First of all, because we do not have a full classification of the complexity like we have for subset repairs. And also because we assume here that when we change a value in the database, we can change it to any value that we want. Okay, but it's not clear what happens when we have a limited domain, when we can use just a limited number of values. We're actually working on this problem now. And it's also not clear what happens when we have a different cost for changing each attribute. Like every attribute has a different cost, or even every cell has a different cost. Okay. So finally, I'm going to talk about another application that we have for the results that we have for computing optimal subset repairs. And here, I talk about a completely different problem, which is the most probable database problem. So the most probable database problem was introduced by Gripkov, Vanderburg, and Sucha, and this is the following problem. So we have a tuple-independent probabilistic database, which means that each tuple in the database has a probability to be selected. And we have a set of functional dependencies. Okay, so in each possible world, we can decide for each tuple if we want to select it, and then the probability is the one that appears next to the tuple, or we want to remove it, and then the probability is 1 minus the probability that appears here. So we are interested in the possible worlds that satisfy this set of functional dependencies. Okay, so for example, this is a possible world. It satisfies the functional dependencies, and the probability of this possible world is just the probability to select tuples 1 and 4 and to remove tuples 2 and 3. So the most probable database problem is the problem of finding a possible world that satisfies the set of functional dependencies and has the highest probability among all such possible worlds. Now, in their paper, they have a result for unary functional dependencies, which are functional dependencies that contain a single attribute on the left-hand side. And they show that if we have a set of unary functional dependencies, then the problem can either be solved in polynomial time or it is NP-hard. Okay, so for example, for A implies B, B implies A, the problem can be solved in polynomial time, but for A implies B, B implies C, the problem is hard. But the problem for general sets of functional dependencies has been left open. Okay, so for example, in our example, we have a functional dependent. The second functional dependency contains 2 attributes on the left-hand side. So it is still not clear for this set of functional dependencies if the problem can be solved in polynomial time or not. So it turns out that there is a reduction from the problem of computing a most probable database to the problem of computing an optimal subset repair, and vice versa. So if you remember this simplify algorithm that I showed you before that we use to decide if we can find an optimal subset repair in polynomial time or not, so we can actually use this simplify algorithm to settle the open problem and to solve the most probable database problem for general sets of functional dependencies. Okay, and I will finish with the result that we have here. So if we have a set of functional dependencies, delta, then if simplify on delta returns true, we can find the most probable database in polynomial time. But if simplify on delta returns false, then it is NP hard to even find an approximate most probable database for any constant or polynomial approximation ratio. Okay, and we get this result because we showed for the problem of computing an optimal subset repair that it is not only NP hard, but also APX complete. Thank you. What? Sorry?
Here you have a fixed set of functional dependencies.
Yes.
It's not fixed. You just have a relation and a certain dependency. What is the complexity?
Okay, so our results, our negative results are for data complexity. So we assume that it's fixed, but the positive result that we have, the algorithm, is actually polynomial also in combined complexity, when we assume that everything is given as an input. I'm sorry, I can't hear you.
What happens if these are in normal form, given in some normal form? This makes life easy. What do you mean?
Yes. Yes. Yes, so that's actually a very interesting direction for future work. What happens when the weights are updated after we change a value.